Last time, in the last few minutes, we argued that the rational numbers are a field. Now, completing this proof is obviously part of the third problem set, but this is basically an algebraic statement about the set of rationals. There's one part that I didn't have time to cover, but we will do that now, which is this isn't just a field, but it's an ordered field, right? There's an order to it. And this is pretty much analogous to what we did for the integers, but let's just write it down for the sake of completeness. Is a field. Rationals form a field. So what about the order? Now, why is the order important? Well, we have been talking about fields before. So recall or notice maybe that the field ZP has no order. Has no order. And by has no order, I mean it cannot be ordered in any way. Cannot be ordered as an ordered field because it is cyclic, right? So the elements of ZP are on a circle. So for example, if you had this inequality, A less than B, maybe we can agree that 2 is less than 5 for whatever reason. Maybe this is Z7. Then we can agree that 2 is less than 5. Then you can just add the number 1 on both sides, which should preserve the inequality if this were to be an order compatible with the algebra. So you keep adding 1 on both sides, but eventually the right side will have to be smaller than the left side, which is a contradiction, right? So the fact that these numbers are on a circle and that they cycle tells you that you cannot really order them. So this is a disadvantage of these fields. The rationals don't have this disadvantage. The rationals can be ordered. And in fact, there's a total order for them, right? It's not just a partial ordering, it's a total order fully compatible with the algebra. So a rational, and recall that rational numbers are just equivalence classes, right? So a rational has a representative A over B. From now on, a rational from now on, let's denote this by A over B, as you might expect, right? This is the new notation. Is called positive if what? Well, either both of them are negative, A and B, they're integers, right? So they could both be negative or they could both be positive, but a succinct way of writing it is just multiply them. And if you get something positive, well, that's what it means, right? We denote the set of all these by Q plus, right? So that's the set of all positive rationals. Now, maybe just as an example, the rational, let's say 2/3 is positive. Now, 2/3 is supposed to be an equivalence class. So I picked the representative 2, 3, but I could have picked the representative 4, 6, which is equivalent if you follow the definition. And by equivalent, I mean that the equivalence classes are equal because these pairs are related under the relationship, right? The equivalence relation. I could also have picked 8, 8, 12, and so on, right? So there's infinitely many representatives for each pair. The same thing happens with the integers, but here it is, I think, a lot more clear what these equivalent relation, what these equivalents mean, right? How these pairs are equivalent. Two pairs are equivalent if they produce the same ratio, essentially. And something that you can prove is that you can always find a representative where it's in reduced form. That is, where these two numbers are coprime. Because if they're not coprime, you just divide them out by the greatest common divisor, and then you get something that is necessarily coprime. So the example, this rational number is positive. We could have picked negative representatives as well, right? Now, the fact that I'm using this fraction notation a over b tells you that I already proved, or at least stated last class, that the representatives don't matter, right? I could pick any representative and all the algebra works out. The order does as well, which by the way I haven't defined. So the definition is, so two rationals, Q and R, right? So let's see, have two rationals. So then the order in the rationals, Q is less than R if R minus Q is a positive rational, right? If you subtract the big one from the small one, then you get a positive rational. I guess I have to rule out the fact that they could be equal, but I can add that in later, right? So this is either positive or zero, but let's just define the strict order. Maybe let's just include it like this. Or they're equal, right? So that's how you define the order, and this is analogous to the integers. So an important remark that this is technically part of the proof of the theorem in the problem set, but I didn't include anything specific about the order, is that this order is compatible with the algebra. Now, I don't want to be too precise in the language with what this means, but you can, I think, guess what it means. It means that if you have an inequality and you add something on both sides, then you still have an inequality. It preserves the inequality. With the product, it's the same thing. If you multiply times something positive, well, then it preserves the inequality and so on. Basically, that's what compatible means. And like I said, maybe I can write it here. Okay, so A less than B implies that A plus N or A plus Q, let's say, less than B plus Q, and also A less than B, Q positive implies that A times Q is less than B times Q, and so on, right? This is what it means to be compatible, that it behaves the way you would expect, and this behavior doesn't happen with the modular classes. So we actually do need the rationals to have an ordered field. All right, so this tells you how to deal with the rational numbers. There's some other important differences between the structure of rationals and other structures that we've mentioned in the past. One of them is the fact that this ordering that I just defined, produces a dense set, right? The rationals are dense. So let me write that down in a more precise way for you. Okay, let me see. Is there anything else I should mention? Okay, so theorem. The rationals are dense, and I haven't defined dense, but I will do it inside the theorem because I don't think we will mention this anywhere else except for the real numbers. Between two rationals, there is a rational. So all the structures we've talked about so far have been discrete, right? Between two integers, two consecutive integers, there's nothing, right? The same thing happens for modular classes, even though then the question doesn't even make sense because we don't have an ordering, but you can still picture them as discrete sets, right? Just isolated points. But the rationals, form a dense set, right? So you have two rationals here, and then you can find a third one in the middle. Then between these two, there's another one, and another one, and another one. So you have like a dense cloud of points. Now, the interesting bit about this cloud of points is that even though this cloud is dense, it still has holes. There's still things that are somehow intuitively in between, but that are not rational. And perhaps the most surprising fact about this, that we will mention in a few minutes, is that the rationals, even though they are dense, they have more holes than points, which is very counterintuitive, especially in a measure theoretic sense, as we might explore maybe as part of the topology chapter, which has a little bit more of detail than the one I want to cover now. Okay, so let x be smaller in the rationals than y. I don't want to add this sub-index every time, right? Eventually we'll be comfortable enough that we can drop the index because we'll know what we're talking about from context. But let's add it now for the sake of formality. So we have two rational numbers, x is less than y. How do you think we can construct something in between? How would you find a rational number that is strictly between x and y? So bigger than x, but smaller than y. And you should feel free to use your intuition, right? So this is x, this is x, and we know that these are somehow sorted on a line. This is y. So how do you find something here? We can actually find something that is exactly in the middle. And let me see the chat. Exactly, so someone already gave me the answer. Exactly, half. We just go halfway, right? So then we have to argue that x plus y is a rational, but that is obvious because we're adding two rationals, right? The rationals are closed in under the operations. That's how we define the operation. So this is a rational. Dividing this by 2 also produces a rational. So this is definitely a rational as well, right? Let's argue. So why is x less than x plus y over 2? Well, one way of doing that is if you believe the remark I mentioned earlier that this is compatible with this ordering is compatible with the algebra, then all we need to do is observe that x is less than y. So x plus x is less than, let's say, a question mark. So since, you know what, I'm just going to drop the index now because otherwise it's going to take too long. X is less than y, then x plus x, because of the compatibility with the order, is less than x plus y, right? I'm just adding x on both sides. Now you'll have to agree with me that x plus x is what I would reasonably define as 2 times x, right? And then I'm done because all I have to do is divide by 2. Dividing by 2 is multiplying times a positive rational, namely 1/2. So x is less than x plus y. So the first half is done. Check, right? Also, how do you argue the other side? Maybe I can just say analogously, x plus y over 2 is less than y. And if you did not understand the proof that I just did, then my suggestion is go over these notes in detail and try to do this as an exercise yourself, right? And that's typically how it works. So indeed, we found a rational between x and y, namely the one that's precisely in the middle, precisely halfway between x and y. So this proves that the rationals are dense, and if you add maybe an inductive argument here somewhere, it's not just true that there's a rational between any two rationals, but there's infinitely many of them because you can keep going, right? Between x plus y over 2 and x, you can also find another rational, and you can find another one and another one and another one. So there's actually infinitely many rationals between any two rationals, sorry. Okay, so here's a property that was proved during the tutorials. theorem. This is called the Archimedean property. This is interesting to me because this can be generalized, right? There's people who study Archimedean rings or other structures that have or don't have this property. So this is certainly something that is not trivial, right? It says that if you have two positive rational numbers, R and S, then for some, you can basically keep adding one of them so that eventually it overtakes the other, right? So there is an integer for some integer, usually a positive integer, for some integer n. And here, of course, with integer, I don't mean just the integer that we defined a few weeks ago, but the integer as a rational number, right? We saw that the integers are embedded inside the rationals. So maybe I can add that here as a comment. So by integer, I mean n over 1. This is a rational number, right? So not just an integer, but I have to make this compatible with the rationals, right? For some integer, we have that if you take the number s and you add it with itself, s plus s plus s, eventually it will have to be bigger than r, no matter who r was. And I will give you some consequences of this theorem. It's not as trivial as it might seem. It actually does. It is useful for certain things. So this is in tutorial. And if it wasn't covered in the tutorials, you can find the solution on the Quirkus as well. So this is tutorial number 5. What was it? I don't know what number it was. Anyway. Okay, so there's one more definition about the rationals that I want to give you, and then we can stop and introduce the next thing. 5, thank you, someone said. Tutorial 5. Okay, so here's something that I'm sure you're familiar with. We define following function. And the function is denoted by two vertical bars and then some number in the middle, right? And this will be a function from the rationals to the rationals. And actually the codomain will not just be the rationals, but it will be the positive rationals with 0, but this isn't really that important right now. So how do we define this? Well, if you have an irrational number q and you put it between bars, then this is defined as either q, assuming it's positive, or 0, and minus q, assuming it is, well, not otherwise. And call it the absolute value. Right, so this is just a very formal way of saying what the absolute value is. The absolute value is you take away the minus sign if it has one, right? You take away the minus sign, right? So if you have a rational is positive, then you don't do anything to it. You get back the same thing, right? As here. If it's negative, then you have to flip the sign to make it positive, force it to be or non-negative rather. So maybe some examples, even though I'm sure this is might even be too easy. So 2/3, the absolute value is itself because it's already positive, right? If you have a number that is negative, like negative 2/3, then I have to flip and get the same, right? If you have an integer minus 7, well then this is just 7, right? And so on. I think maybe this wasn't even necessary, but just in case you haven't seen the absolute value before, then this is how it works. So here's a theorem that you should feel comfortable proving. That I won't do this because it's simple enough, I think. For any x and y rationals, the following happens, right? So first of all, the absolute value is always non-negative, so it's always at least 0. This follows immediately from the definition and the definition of the number 0 as well. Multiplying things inside the absolute value is the same as multiplying them outside and taking the absolute value first, right? the absolute value somehow commutes with the product. Now, this is perhaps the most important property. If you add two things and take the absolute value, then you get this strange inequality. This is the triangle inequality, right? And that one also follows from the definition. You may need to separate into a few cases. And something that follows from number 3 is that if you want to calculate the difference between two numbers already put in absolute value, then this will be at most the difference between the numbers not put in absolute value. This is also called the triangle inequality because these two are actually equivalent, right? So x minus y in absolute value is literally the distance between x and y. And the absolute value is also called a norm, right? So there's a bunch of definitions here that you can find in a more abstract sense. What does it mean for something to be a metric space or a normed space or stuff like that? If you're interested in that, you can look these up, or we can mention some of them in the topology chapter. We will get back to this in more detail as well once we cover that topology thing. But for now, I want to talk about something really interesting. So this is very important, and it's a very broad subject. So we won't have time to cover everything in detail. But of course, the idea is not to cover every single fact about Cauchy sequences. This is an excuse for us to learn how to write proofs in a much more, let's say, difficult setting. It's not really that it's difficult, but there is somehow a conceptual jump between things we've done in the past and these things, right? Everything we've done so far is discrete, and you can usually write down some examples and sometimes even use the computer to approximate things or even solve things using the Chinese remainder theorem and so on. But here things become continuous. So it's a different way of thinking, right? And this is important because you will need this for most courses that involve, let's say, real analysis, introduction to real analysis, like 337. So we will use this as an excuse to learn new proof techniques, but it's not that I want to give a comprehensive course on Cauchy sequences, right? Because this will be very useful for you for many other courses. And it is also the way we are going to construct the real numbers, which is considerably harder than any construction we've done so far. So Cauchy sequences on Q. So let's do everything very clean and carefully, and see where that leads us. Like I said, we won't have time to cover everything. This chapter is probably bigger in my mind than everything we've done so far combined, right? So let's just do the bare minimum so that we can construct the real numbers and use this as an excuse to write down proofs, right? If you understand proofs with Cauchy sequences, then you will also know how to do proofs using limits and involving limits of sequences and so on, right? So this is very, it gives you very transferable skills to other areas. It's my point. So let me define this object for you. A sequence of rationals, but of course you can define sequence of anything, right? Sequence of any object, but let's say of rationals is a function. So any function that takes the natural numbers and outputs a rational is called a sequence, right? And the notation for sequences is as follows. So if this function is called, typically we will call it x, right? Then x sub n is basically the image of n under x, right? So before I give you some examples, or actually, I might as well give you one now. Sample. So what is an example of a sequence of rationals? Well, you can have something like this, I guess. You can start x of n, or equivalently x sub n. You can define it as 1 over n. That is rational, because n is a natural number, and 1 divided by a natural number. Okay. For n positive. and x sub 0, let's just say that this is 0, right? So this is a sequence. It's a sequence of of rationals. And how does the sequence look like? Sequences should be thought of as this. So you have the index 0, 1, 2, 3, so on. And on this side, you have all the rationals. So the first one is 0, right? So it's a point over here. And the next one is the number 1, 1 over 1, then 1 over 2, then 1 over 3. And you get this sort of descending curve, right? So that's what this sequence looks like. And it approximates, of course, as you'll know, the number 0. Why does it do that? Well, you do need the Archimedean property to prove this formally. But we will do that in a second, right? Now, there is a flaw with Q. There are things that we still can't solve. For example, even though we can solve everything of the form AX equals B, when A is non-zero, how do we solve this? Well, we can just divide by A and get this rational, right? So that's how we can solve this every time. I'm not writing this down again because we already argued why this is true in fields in general when we were talking about modular fields, right? But there's a new flaw. X squared plus 2 equals 0 has no solution. Has no solution. So let's prove this. Proof. How do we prove that this has no solution? So suppose there is a solution. A divided by B, right? Then A divided by B squared is equal to, actually, I wanted to write a minus here, right? Otherwise, it also has no solution, but for a different reason. Yes, thank you. Someone in the chat already pointed it out. I wanted to write a minus. So this is equal to 2, right? If I just solve for the number 2. Right? So this means from here, so yeah, like I said, if I have a plus there, it still has no solution, but the reason is different. So I want to include the minus. From here, a squared is the same as 2b squared, right? Now, something that I should have mentioned, I mean, I did mention it, I just didn't write it down, is that every rational number can be written of the form, you know what? Let me just add this for the sake of completeness. So like, I should have mentioned this earlier, or when I say mention, I should have written this down before, but let's say that this is like a lemma that you can obviously use. So for every x rational, right? There are a b coprime such that a divided by b is x, right? So for every rational number x, you can always find a fraction a over b where a and b are coprime. And how do you prove this? This is actually very easy. Just argue that if you have two numbers a and b and you divide them by the greatest common divisor, you divide out every divisor they have in common, what you get will have no divisors in common because you eliminated all of them, right? So what you have to argue is basically that the greatest common divisor between a divided by the GCD AB and b divided by the GCD AB, then these are always coprime. Why does this work? Well, this follows immediately from Bezout's lemma, right? So actually, this is actually a good exercise. Then a divided by b, this fraction is the same as a divided by the GCD divided by b divided by the GCD, right? So this is a rational, but these two numbers, the denominator and the numerator, are coprime. So regardless of who A and B is, you might need to assume they're positive and then add a minus sign to make this work. So maybe let's add a small plus there, just so that the GCD is well defined and stuff like that. But of course, you can easily generalize this. These two numbers are coprime, right? So regardless of what fraction you start with, A over B, you can always find a representative where they're coprime, right? So completing this is the exercise. Let's say complete this proof. It's a very short proof, right? If you want a hint, is whenever you have to work with coprime numbers, like I said, always use Bezout's identity, right? So that's another exercise, and it's good practice because it combines two things. It combines number theory, things about coprime numbers, and it combines things about the rationals, right? So suppose there is a solution, and now we can add this. We can now add this. So A is coprime to B, right? We can always find numbers that are coprime. So regardless of what the rational A over B is, we can assume that it's already reduced, right? The way we did up here. Just divide it by the GCD and it must work. Okay, so like I said, A over B squared is 2, from which, from here, A squared is equal to 2B squared. You've probably seen this proof before. Now, A squared is even because it is 2 times something. But 2 is a prime number, right? So by Euclid, A must be divisible by 2. So A is even. And if A is even, then it can be written as 2 times K for some K, right? So what do we do now? Well, we can just plug everything back in, right? So A squared, which is the same as 2K squared. Sorry, let me put this in the middle. We agreed that this was 2B squared, right? But squaring something of the form 2K is 4 times K squared. And this is a big problem because it means I can cancel out 2. I can just divide everything by 2, right? So 2K squared is the same as B squared. So by the previous argument, using Euclid again, B must be even. But this contradicts the fact that A was not even. Sorry, they can't both be even at the same time because they are coprime, right? We chose them to be coprime. And even if we didn't choose them to be coprime, we could keep going. We can do this over and over and over again, showing that these two numbers, regardless of what they are, will be divisible by infinitely large powers of 2 or something like that, right? So if we start with numbers that are not coprime, well, you say, okay, they're both even. That's nice. So divide them both by 2. Then you get the same fraction. And you repeat this process. Then you must be able to divide them by 2 infinitely, which is, of course, absurd. But a shorter way of writing this proof is just assume that they are coprime to begin with. We can always do that, right? We can always find a reduced fraction. We already did this in the example up here, right? Where was it? The example up here, somewhere. Okay, the one you can see at the top of the screen. If you have a fraction of the form 8 divided by 12, you find the GCD, which is 4. You divide it out. So 8 divided by 4 is 2, and 12 divided by 4 is 3. So this is equal to the fraction 2 over 3, and 2 and 3 are coprime. So you can always do this. It's nothing too obscure. Okay, so this is interesting because it shows that the square root of 2 is not a rational number, right? There is no square root of 2 in the rationals, right? So another way of thinking about this is that if you take the set of rationals, let's call it Q, whose square number is less than 2, whose square is less than 2, then this set is bounded, right? Because you can obviously find square numbers that are bigger, square numbers that are bigger than 2. 2 times 2 is already 4, which is bigger than all of these, right? So this set is non-empty, non-empty, and bounded from above. But it has no uh, it has no supremum. So this is something that we will cover in more detail as we construct the real numbers, right? No supremum, that is, the supremum is the lowest higher upper bound, lowest upper bound, right? So the rationals have like a bunch of holes in them. Every square root of a prime number, by the same argument that I just used, will be a hole. But there's actually a lot more holes than that, and we will prove that using a counting argument. Basically, the rational numbers have more holes than points, even though it's a seemingly continuous or at least dense line, which is very counterintuitive. But to understand this, we have to cover a little bit more theory on these sequences. Let me give you the most important definition of today's lecture. A sequence x sub n is Cauchy, and that's not a very nice notation. Okay, you know what? Let's just write it like this. So let's say x, because I want to be able to mention what the index is when I'm talking about a sequence. So let's just do it the way people do it everywhere, and you put them in parentheses and then just add the index like that, right? Some people even add more details, like from n0 to infinity or whatever. So a sequence is Cauchy if the following happens, right? For all epsilon positive rational, and we will typically think of this as a very small rational number, there is, and this is, like I said, where the conceptual jump might come into play, right? There is a natural number such that for all, right? So starting with n0, every index bigger than 0 satisfies the following. For all nm bigger than n0, the distance between mn and xn is bounded by epsilon. So this is what it means to be a Cauchy sequence. So what is the intuition behind this? Let's do some abstract examples to see the intuition for this, right? So what does this all mean? So maybe let's make like a big graph here, right? And these are the indices n, and this is the rationals, right? So this is how a sequence looks like. So the sequence can be very chaotic at first, can jump around, but eventually these numbers have to approach each other. That's what it means to be Cauchy. Now, I'm not talking about limits here or anything, right? In fact, this doesn't mean they have a limit. The sequence could still diverge. This is slightly more abstract in case you've seen calculus classes. I mean, this is a very common generalization, or not generalization, but a characterization, right? So this is a sequence x0, x1, x2, and you get the point, right? So whenever I challenge you to give an amount epsilon, you should be able to produce a boundary, n0, from which onwards every distance is bounded inside this epsilon, right? So regardless of which points you take, if you measure out the distance, it's going to be smaller than epsilon. So the sequence becomes closer and closer to itself. Now, this is very similar to the way that you define a limit of a sequence. The advantage of doing it the way I'm doing it now, which is going to be slightly different, by the way, is that here I don't have to tell you what the limit is if it exists, right? I'm not saying the limit is L for some real or rational number L. I'm not telling you that at all. I'm just saying these numbers approach themselves. If they approach a fixed number, well, that's a matter of I don't want to say debate. You don't really debate in mathematics, right? But I think you get the point. If these numbers will approach a fixed number L, that is a different matter, is what I'm trying to say, right? Okay, so any questions so far? Okay, so that's an interesting question. Someone is asking, Cauchy sequences are equivalent to convergent sequences in a complete field. The answer is yes, but it might either be something trivial in the sense that that's how you define complete fields, or it might be something really difficult to prove, depending on which definition of complete field you use. Most people, like I will do that in this context, will define complete field by saying that it's when these two things are equivalent, right? Cauchy, if and only if convergent. Yeah. Okay, so why do we care about this? Maybe let me tell you a little bit like a spoiler on why this is going to be useful for us. So the reason we need to define Cauchy sequences is because there are sequences, such as anything that approaches the square root of 2, any sequence of rationals that approaches the square root of 2, that one is not convergent, right? Because we just argued the square root of 2 is not a rational. It's not something inside the field Q. So this will not be convergent. The limit is outside, right? So we must be able to talk about these holes without explicitly saying what those holes are because we don't have anything to talk about them, right? We haven't defined the object that is missing. So one way of talking about that is by using Cauchy sequences because like I said, a Cauchy sequence is like a convergent sequence where we don't specify what the limit is. I'm just saying these numbers approach each other, right? So if you had a sequence that approaches the square root of 2, of rational numbers, then it would be a Cauchy sequence, but there's no need for me to tell you what the actual limit is because I can't. There is no square root of 2 in the rationals, right? I haven't constructed that. Okay, so what do I mean exactly by holes or something missing? That's a good question. So here, let me give you a more specific example of what a hole is. Actually, I can use this very same example, right? So these are the rationals. And right here, somewhere, is the square root of 2 as a real number. And by square root of 2, I mean, of course, the lowest upper bound of this set of rational. Where is it? Sorry, at the top of the screen, you can see a set that I defined. All rationals, such that when you square them, you get something smaller than 2, right? So this number has a lot of upper bounds. It has 4 is an upper bound, right? Because every number like this has to be less than 4, for example. It has to be less than 2 as well, by the way. Anyway, if you look at all these bounds form sort of a convergent sequence if you find a lower and lower and lower bound. But there is no lowest upper bound. So it is like as if the rationals had a hole where the square root of 2 should be. But we can still think about sequences of rational numbers that approach this square root of 2, even though if I define it as a Cauchy sequence, there's no need for me to tell you what the limit is because, well, I can't. I haven't defined the square root of 2. In fact, all I did is do the opposite, right? I just convinced you that the square root of 2 doesn't exist in the rational numbers. So that's what I mean by holes. There's things that are sort of missing, like the square root of all these primes. Now, right now, I only have a handful of examples of things that are missing, but once we develop a little bit more theory, you'll see that actually almost everything is missing. The rationals are countable, right? There's as many rationals as integers, but the real numbers are not. there's so much more real numbers than there are rationals. So most of the things that are on the real line are wholes of the rational numbers. The rational numbers are like a minority there, even though it seems very counterintuitive because I only now just define these things. So that's why I'm not writing these things down. Okay, so why don't we do before the pause, give one example of a Cauchy sequence. It's the one that is today's quiz. You can also already find it on Quarkus, I believe. So let's prove that something is a Cauchy sequence. Sample. And I think the easiest example I could come up with is show that xn equals to n plus 1 over n is Cauchy sequence. This is not an interesting Cauchy sequence because this is actually convergent, right? Converges to 1. If you take the limit to n to infinity, then this is basically infinity over infinity, but they both approach the same rate. So this is just 1. But let's prove that this is Cauchy. Show that is Cauchy. So let me help you, start you off by the proof, and then you can write this cleaner. And this is today's quiz. So what you do is you pick a positive rational number epsilon, and now you need to produce an n0, right? The definition says for every epsilon positive rational, so I grabbed one already, an arbitrary epsilon, there is an n0. So how do we find that n0, right? So how do we do that? That's the question. So the thing that makes these proofs challenging to come up with is that they are, unlike other proofs we've seen so far, they are written in a very different order than they are thought about. Because right now, then I should be able to tell you what n0 is, but of course, how am I going to guess that if I don't even know what I want to get, right? So these proofs are thought about in a different order. We have to first pretend like we already know what this n0 is, and at the end we fill in the details, right? So let us just do that right now. So eventually, what I want is to bound this number, right? For nm bigger than whatever n0 I will define for you in a second. I will actually not be able to tell you exactly what it is equal, but you'll see how to choose it right here, right? So for nm bigger than n0, what we want is this number to be bounded by epsilon, right? This is what we want, but we don't know how to do that yet. So what if we just plug in this number by definition? So this is just m, let's see how this works. Shouldn't this be m minus n divided by mn? Actually, that's the other way around. I think this is just n minus m divided by nm, but correct me if I'm wrong. Right, another way of writing this is just 1 over m minus 1 over n. Right, they cancel out if you just simplify this. Now, what can be said about this? What is the difference between those two numbers? Can certainly write this in terms of just n and m, right? Because the distance between these two numbers is always less than whichever fraction is bigger, right? And the bigger fraction is the one produced by the smaller number. So this happens. So that is true. So since this happens regardless of who n and m is, all I have to do is bound this number by epsilon, and then I'm done. Now the question is, of course, how do I do that? Actually, we can do better than that, right? Because this is not only true, but if you find the minimum number, this is always going to be smaller than 1 over n0, right? Because regardless of who m and n is, they're bigger than n0. So the fraction is always smaller. So all we have to do is bound this number by epsilon, and then we're done, because then I bounded this by epsilon as well, right? So this is how you would think about a proof like this. Actually, I already solved half the quiz for you, so let me give you 10 minutes to think about this. Pause recording. Okay, so once we got this far, how do we find what n0 is? So what we want is this. We want this to be smaller than the epsilon we chose, right? And notice that this thing that we want will happen if and only if the following happens, right? Um, what um, what n0 could we choose? So all we have to do is choose an n0 that is larger than what? So just choose any natural number that is larger than 1 over epsilon. I think maybe I have to add a 1 here. We can do that, right? So we fixed epsilon. So this is a rational number, right? So using either the Archimedean principle or just your common sense, the natural numbers are unbounded, so there must be one that is bigger than this fixed rational number, right? For example, the ceiling. Someone mentioned in the chat, actually, now that I think about it, we could have used it here, right? So the n0 could be the ceiling function of 1 over epsilon plus 1, basically rounding up the number, for example, but there's no need for that. But yeah, that's still a good idea. This looks like a point. It's 0, right? Then why does this work? Well, if this is true, then 1 over 1 over epsilon over n0 would be smaller than 1 over 1 over epsilon, which is of course epsilon, right? So we did this in a sort of reverse engineering kind of way. And this actually concludes the proof. So xn is Cauchy because we took an arbitrary epsilon and I produced an n0 that obviously depends on that epsilon that works. We will do many more examples with Cauchy sequences, so don't worry if this is still new or unfamiliar to you. There's plenty of things to explore, probably even too many things. There will be things that I will just have to tell you. You can prove this. This is how it works, and you can use this for the problem set because it gets quite lengthy as well. Okay, so here's a lemma that's very important that you may have heard about if you've taken other courses like 137 or stuff like that. Cauchy sequences are always bounded, right? They may not always be convergent, but they are always bounded, right? So if xn is Cauchy, then there is a bound. There is, let's call it delta, positive rational number such that for all n, the absolute value, everything lies in between this delta, right? This makes sense from the drawing I did up here, right? If it is true that these numbers approach each other after a certain point, then all I have to do is bound these finite numbers here by something large enough, and then make sure that that bound works for the right-hand side as well. And then I have bound everything, right? By bounding, of course, I mean finding a ceiling to everything, you know? So how do you prove that? That such a sequence cannot be unbounded. So for example, xn equals n cannot be ever a Cauchy sequence because it's unbounded. It doesn't approach each other because it doesn't approach anything, right? Okay. So how do we prove this? And like I said, this is where proofs get a little bit more, there's a bit of a conceptual jump. So make sure you review this in your own time. If this is unclear, if this is the first time you're seeing these sorts of proofs. So the proof is actually what I just explained. There's two things we have to do. We have to bound the numbers that eventually approach each other. That's easy because for every bound that I impose here, eventually they will be that close to each other, right? And if I do that from some point onwards, then the points that were before that, there's just finitely many points, so I can just bound them individually, right? Delta could be something really large. It doesn't have to be a small number. It could be any number. I'm just saying that there is a bound for this, right? So any bigger bound would work as far as the theorem is concerned. Okay, so taking epsilon 1 in the definition of Cauchy, because we know it's a Cauchy sequence, right? So if we take epsilon equals 1, we could have picked any number. We could have picked 100, a million, whatever, but 1 works just as well. So there is a threshold n0 such that for all the numbers that are bigger than n0, the distance between these two cells right here, and xn, is bigger than epsilon or bigger than 1, right? So I can definitely make sure that if I pick this threshold as 1 instead of epsilon, then there's some point at which they all approximate each other by that amount. And then I just have to worry about what about all the indices smaller than n0. But those I can just treat separately, right? So then just take delta as, well, how do I do this? Well, I have I have to find a number that's bigger than x0, the first element of the sequence, bigger than the second element of the sequence, actually bigger than all elements of the sequence until the threshold, because before this they might not be bounded by 1, right? This is an n0. Hope you can see that. So what I take is I can take the set. This is a finite set, so just pick the largest one, and maybe add 1 to make sure that delta is also bigger than 1, in addition to being bigger than all of these, right? So then there's two cases, because I argue that delta works. Delta is a bound for the entire sequence, but there's two cases. Indices that are after n0 and the ones that come before. The ones that come before are obviously bounded because that's how I defined it, right? So if some index is smaller than n0, then it should be obvious, but let me know if it is not obvious, that this is bounded by delta. Because delta is the biggest one of all of these, even plus 1, right? So it's obviously bigger than this x0. So this works. If, on the other hand, n comes after n0, or maybe even, let's say that this could be n0, right? Just to cover every single index. When this is bigger, then what happens? Well, if this is bigger, we know, someone writing in the chat? No, okay. We know that the distance between xn and the last one to be inside the threshold, which is this one, this is smaller than 1, right? Smaller than 1, because that's what it says up here. And then you can just apply the triangle inequality and those sorts of things to prove that xn itself must be smaller than x sub n0 plus 1. And this was chosen to be smaller than delta, right? So in other words, xn is smaller than delta in all cases, for all n. So it is bounded. It is bounded by this delta that I just came up with, right? This is a very useful property because it rules out many sequences as not being Cauchy, right? All the ones that are unbounded, there is no chance of them being Cauchy. Now let me tell you an important definition. So if you have two Cauchy sequences, so let xnn and yn be Cauchy, then the following thing is defined, right? So how do I add two sequences? This doesn't require too much imagination. To add two sequences, just add each term individually and form a sequence. And to multiply two sequences, I'm defining the operations on the real numbers, by the way. This wasn't clear. Just multiply them term-wise, right? Does that make sense? So a lemma that you can just assume this. It's really technical. We've skipped these sort of technical arguments in the past. You should only prove this if you're feeling very motivated to working with Cauchy sequences. These are also Cauchy sequences. And by these, of course, I mean these, right? So the sum of two Cauchy sequences or the product of two Cauchy sequences is also Cauchy. This is unfortunately kind of technical, so I don't even want to leave this as an exercise because there's a risk you might think that this will be on the final exam. It won't be, right? This is kind of a lengthy proof, but I promise you it uses nothing we haven't already seen. You have to find a bound, right? You have to use the previous lemma, the fact that these all of these sequences are bounded, to bound them and then do a clever manipulation of these things. So let me just add this as an exercise. There's nothing obscure going on here, but it's kind of a long proof. So exercise, and this will not be on the final because it's too long to be on the final. My philosophy for the final exam is the exercises should have more or less short solutions, things that are similar to things we've either left open in the lectures or the problem sets. And this lemma doesn't fall into that category, right? It's probably longer. It's longer than this lemma for sure. This one's quite short. Maybe twice this length for each of these, right? Anyway, do try to solve them in your own time, especially if you're struggling to understand Cauchy sequences. This is a very useful thing to solve. And it is also quite important because it contains the key to understanding why, for example, adding two continuous functions produces a continuous function, right? So this is not just about Cauchy sequences of rationals. The same idea, the same proof works in a much more general setting about real numbers. So I've told you how to add them, how to multiply them. There's a bunch of more things that we have to cover. But basically, I can already tell you what a real number is. So let me define the following thing, right? So definition. Okay, so people are asking me about the difficulty level of the final. So like I said, my philosophy for a final is it should be slightly harder than the easiest questions in the problem set. Those are probably way too simple for a final. But they shouldn't be harder than the harder problems, right? So something in between, something that should feel more or less familiar to you. So my idea is if you solve the entire problem sets, all of them by yourself, and you understand them, including the additional exercises, you should find the final exam easy, right? Because otherwise, what's the point of having a final exam? Anyway, we can talk about that more later. We will host review sessions and plenty of time for you to prepare. But for now, let's focus on this. So, okay, so let xnn and y. These will be the representative of the real numbers, right? Every real number can be approximated by rationals. So if you take two Cauchy sequences, actually just two, yeah, let's make them Cauchy, otherwise it doesn't make sense. Let P Cauchy sequences of rationals. Then we define xnn is equivalent to y and n if they approximate each other, right? If for all epsilon positive rational, there is n0 n such that for all n bigger than n0, these approximate each other. So xn minus yn, we can use the same index here, it doesn't really matter, is less than epsilon. And a lemma that you should be comfortable enough proving is that this is an equivalence relation. and I think you can see where I'm going with this, right? The equivalence classes of this equivalence relation, those are the real numbers. But notice that this is considerably more complicated than what we did in the past, because in the past we had tuples, right? Every representative of an equivalence class was just a tuple or a pair of naturals or a pair of integers. But now it's not a tuple, it's a sequence of rationals. So it is considerably more complicated. Now you need infinitely many rationals to represent a real number, even though in the past all you needed was two of the previous object to represent the new object, but now you need infinitely many of them. So this should tell you that between the real numbers and the rationals, there is a bit of a jump, not just a conceptual jump in terms of understanding what it is we're doing, but like a theoretical jump. Like there's a wider gap to be bridged between these two objects. Okay, so this is an equivalent relation. That's not a difficult thing to prove, so I will actually leave this as an exercise as well. It's good practice for Cauchy sequences and equivalence relations, even though we've done plenty of that in the past. And then a remark that is not interesting at all, but you can also prove that if you want, is that so this relation, let's say if we have an equivalence class of xn, right, under this equivalence relation, and I want to add it to another equivalence class, apologies, then one way to define this is, of course, we already know that if you add two Cauchy sequences together in this fashion, we get a Cauchy sequence. So this is a valid class, right? And the same for the product. Maybe we can just copy paste that in. And this is how you add, and okay, that's not at all what I wanted to do. This is how you multiply and add and multiply real numbers together. Just pick a representative and do this. So the remark is that this is well defined. And I've used the term well defined every single time I've defined an equivalence relation and constructed a quotient in this form. So I will not rewrite it in this way. I won't even add this as an exercise because this is fairly routine arguments by now. I'm not saying those are easy, but you can just assume that this is true for the problem set. Okay, so now we can just define what a real number is, right? So a real number is an equivalence class. Right, so you pick a sequence under this new equivalence class being sort of Cauchy equivalent. And that's basically the idea. Okay. Now there's a bunch of intermediate lemmas that you might need. You could take this more as a hint for how to solve the problem set, because working with real numbers is a little trickier, right? It requires a different approach, a different way of thinking. And by the way, there's also a way to order. How do you think you would order these? Maybe let's start with that. So I've defined the algebra to you, and every rational, the same way we did before, that the integers are part of the rationals and the naturals are part of the integers, then we kind of also want the rationals to be part of the real numbers, right? So every rational corresponds to an obvious Cauchy sequence. Right? How do we show that the rationals are sort of contained in the real numbers? Right? So if Q is a rational number, then how do I find a real number that will correspond to Q? Because we want the real numbers to contain the rationals, right? So what do you think? What Cauchy sequence would you suggest? So as before, the rationals are contained, right? There is a function f from the rationals to the reals, right? That preserves all operations in the same way that we already did this in the past. The structure, so the order, the addition, multiplication. I haven't told you what the order is yet, but you can maybe guess what it is. So what Cauchy sequence will correspond to this rational number q? What do you think I can pick here? Well, I have to pick some sequence index. What would you do? Exactly. So every term is just q, right? The constant sequence of just q. That one is a sequence of rationals, obviously. It is also obviously Cauchy because the distance between any two numbers in the sequence is zero. They're just the same. It's a constant sequence, right? So this is one way to do this. It's not the only way. You could have picked many other ways of doing that, right? Same as before, right? We also had infinitely many ways of representing the previous structure in the new structure. So something that I haven't mentioned, which maybe we should, is how do we order these sequence? When is a sequence bigger or smaller than the other? So we will do this analogously, right? To define the order in R, we define a Cauchy sequence xn from 0 to infinity is positive. If what? How would you define what it means for a number to be positive? It has to sort of point to a positive number, right? So if it's rational, then it has to be a positive rational. But if it's not rational, we still want this to point to something rational, right? So we can say that for some n0, then after a certain point, all of these numbers are positive, right? So for all n0, xn is just, let's just say positive, right? As rationals. This is the order of the rationals, obviously, right? That's what it means to be positive, and then we say that a real number x or a sequence x is less than or equal to a sequence y if they are equivalent, if they're equal, that is, or if subtracting the bigger one, sorry, subtracting the small one from the big one is positive, right? And that's how we define the order in the real numbers. Maybe I can just add it like this. And this is the real numbers. In that case, I can just say they're equal, right? The classes are equal. So I know if it's the first time you're seeing this sort of thing, it might seem quite abstract. So I strongly suggest that you do review this in your own time, calmly, right? Let me add another lemma that you might find useful, and this will work as both practice and it will also simplify your task, right? So suppose that we have a real number. So we have a sequence xn that is not equivalent to the sequence 0, the rational number 0, essentially, right? So you have a non-zero number, then there is y, Cauchy, such that x times y, maybe I should just write the number x here, right? X times y is equivalent to the sequence, constant sequence 1. And this tells you that the real numbers are a field. This is the most important part, right? You have a non-zero number, or non-zero real number x, then there is a y, also a Cauchy sequence, such that x times y is 1. So y is the inverse of x whenever x is non-zero, right? So we can read this. So this means that as real numbers, y is the inverse of x. But of course, not right now, we are not talking about real numbers yet. We have to prove this in the context of Cauchy sequences. So any questions? Let's prove this as practice. Okay, so each real number is defined by a specific Cauchy sequence. So there are many Cauchy sequences that will define the same real number. That's actually a really good question. So remember, in the past, when we defined the rationals as, pairs of integers, there were infinitely many pairs of integers that produced the same rational, right? Basically, 2 over 3 was the same as 4 over 6. There was infinitely many integers that would define the same rational. The same thing happens here, but here it is maybe a lot more difficult to see why, but it is also not impossible. So let me maybe add this as a comment answering chat so that it makes sense for people just reading this, because this is kind of outside of context. So answering the chat. So that's a really good question. Let me convince you that I can produce infinitely many Cauchy sequences for the same real number. So there are actually there's more than infinitely many Cauchy sequences defining the same real number. Let's do this with a sketch. So let's suppose that you have a Cauchy sequence that's defining a real number, right? So these numbers approach each other, but of course, what we want this to be in the end is we want this to approach the real number, right? This is the real number represented by this Cauchy sequence, intuitively. So one thing you can do is you can just cut it off at the beginning, someplace. Maybe this is like the index number 5 or whatever. And then you change these numbers to whatever you want. That will not change the limit. It will not change the fact that this is a Cauchy sequence. And it will not change the fact that this Cauchy sequence is representing the same real number. Right? The only thing that matters for these sequences is what happens eventually. So I can cut it off at the beginning, at the tail, and do whatever I want with the first few terms. So one thing I could do is, for example, I could take this number x and add n to it. And then for every number n, you get a different Cauchy sequence, but they are all equivalent. They are all equivalent under the same definition. Hopefully this makes sense. Okay, so here's a question. Is the number of ways that we can represent this uncountable? That's a good question. The number of ways. That's a good question. Let me think about this for a second. Yes. Yes, it is. Actually, sorry, let me double check that. That's a tough question. So there's uncountably many Cauchy sequences, but for a fixed real number, I think there's only countably many. At least the construction I gave you right now will only produce countably many ways of constructing the same fixed real number. But there might be more ways. This is not the only way, right? This is not the only way. So yes, to answer the question, using the construction I just gave you right now, I can only produce countably many different ways. And my intuition tells me that you cannot find more than that. But there are uncountably many Cauchy sequences of rationals, so maybe there is a way. Yeah, that's a good question. Yeah. Okay, so in the last few minutes, let's maybe try proving this rather difficult lemma right here. So proof of lemma. And by the way, let me add this as a comment because I didn't write it down. So this lemma is the key to showing R is a field, right? So how do you prove this lemma? So the lemma is saying you have a sequence that is non-zero, and then you must be able to find another sequence such that when you multiply them together, you get 1, right? Okay, so since x is not 0, right? Not the sequence 0, there must be a positive number, positive real number, positive rational number, and some threshold and 0 natural, such that these don't approach 0, right? So they are bigger than epsilon, because otherwise they would be approaching 0. So eventually, you can always find a positive distance between xn and 0, right? That's just the definition of being a Cauchy sequence. So now consider the following. The following sequence. We just consider xn, let's say prime, to be the constant epsilon if n comes before the n0, and xn prime will be the same sequence if n comes after n0. So we've essentially cut off the sequence and made it constant for the first few terms. And afterwards it can just be the same sequence. It doesn't matter, right? This is just to guarantee that, well, you'll see why in a second, right? So then xn is Cauchy sequence, of course. It is a Cauchy sequence because xn was already a Cauchy sequence to begin with, and I only changed the first few terms, made them constant, right? But more than a Cauchy sequence, something that is very easy to verify is that these are still equivalent. It's the same. I found a different representative. It's actually the same idea that I just wrote down. This was kind of lucky. So if you have a Cauchy sequence and you change the first 1 million terms to whatever you want, you have a sequence that is still Cauchy, and moreover, it's still equivalent to the first one, right? You found a different representative for the same real number. So this was actually pretty lucky that someone in the chat asked me about this because it is the same idea we're using now, right? Such that, so in particular, since they are equivalent, they satisfy the same thing eventually, right? So xn is also bigger than epsilon for all n now, right? So I managed to isolate the possibility of xn being 0, and I made sure that it is always positive, right? It is always above, or not positive, but it is always a distance of epsilon from 0, right? Not just eventually, but all the time, because I cut off the first part where it could have been 0. Okay, now let me think about this. Okay, we're almost done. We're almost done. So since in particular xn is never 0 because I isolated, right? I removed that possibility. Well, we can just consider the sequence yn to be 1 over xn, as you might expect. Is well defined, I guess, or makes sense. So that's the sequence of rational numbers, and it is Cauchy. It is Cauchy because the original one was Cauchy, right? Should we prove that it is Cauchy? Why not? It's Cauchy. So indeed, how do you prove that this is Cauchy? Now, I already used the letter epsilon, so I should use a different letter. So let's say eta is a positive rational number, right? So since the x prime n is Cauchy, there is a number, call it n1, natural number, such that for every index or indices bigger than n1, these approach each other, right? So xn prime n is smaller than whatever number I want. Whatever number I want. Question. We just said xn is not equivalent to the zero sequence. Yes, that means that xn is still possibly 0. That is true. So if you start, you could, for example, here, I could, something I could do if I'm very sneaky. Let's say this x real number is non-zero. Something that I could have done is I could change this initial segment of the sequence and add a bunch of zeros to it, right? I can just delete all of this here and add a bunch of zeros. This is still Cauchy and it is still not equivalent to 0, but it has a bunch of zeros in it. So this is a risk that we have to eliminate by cutting it off at the beginning, cutting off the initial segment and making sure it is positive. For example, picking the number epsilon works because I want this to be at least epsilon everywhere. Now, for the purpose of time, I think I will just tell you what this number is, the one that works, but we will see in a bit why this works. Eta times epsilon squared, right? So why does this work? Well, given that x n prime, like we chose it to always be at least epsilon, right? Always be epsilon distance away from 0. So given that this happens, what happens if we take this fraction right here? So x n, this is always smaller or equal to than 1 over epsilon squared, right? Multiplying those two numbers, because they all have distance epsilon, will always be something positive, even if the x primes are negative, right? They need to have the same sign. They need to be on the same side. So this is always at most 1 over epsilon squared. This just follows directly from what I wrote down earlier. So then, and this is where you would figure out why this is the number that works. So then, and to finish this off, what is the distance between yn and ym? Right? What is this distance? So I define this to be 1 over x prime m minus 1 over x prime n. And if you work out the details using this thing above here, where did I define the eta for the first time? Oh, there it is, right? So this will be smaller than eta, which is the number I started with. From where y, did I call this y? Let's just call this yn, is Cauchy. And x times y is equivalent to 1 under this Cauchy thing, right? Prime. Okay. Let me add one more detail. Now, this, I agree, is a bit of a lengthy proof. This is because x is equivalent to x, right? So you can just swap it out using the fact that the operations are preserved. So this is the full proof. I keep forgetting to add these squares. So this is the full proof, but an exercise would be to read this over carefully and make sure you understand it. Make sure you understand it. Like I said, there's a bit of a conceptual jump here. So if it's the first time you're looking at these things, we defined everything in this lecture, right? So it's a bit overwhelming. So my suggestion is look at these notes, look them over. And on Monday, instead of me just giving you a huge list of more things, we can just finish the construction of the real numbers. I can tell you what you're allowed to assume and what you're not allowed to assume, maybe give you some hints as to how to prove this. But please make sure that you read this over the weekend or the next few days so that you have questions for me. Let me stop the recording.